So welcome to the last part of lecture 25. There's kind of one piece though that we need to do, which is kind of talk about the proof of this result. Now you can find the proof in the book, but I wanted to kind of just quickly go over the main ideas so that maybe it will help you when you're reading the proof to understand what's going on. Okay, so let's go to the relevant part here. Okay, so I'm just going to sketch out the main ideas. So one thing we want to notice is that if we have a nilpotent operator on V, then N maps V onto the range of N. But then we can apply N, this is a subspace, and we can apply N to the range of N, and that maps it into the range of N squared. And we can keep doing this, okay? We keep going, and the claim is that if you keep doing this enough, eventually you end up with 0 for some range t. Right? The range will keep getting smaller and smaller and smaller. So you look at range n, you range n squared up to range t. Okay, and in particular, if m is the largest integer such that the range of nm does not equal the 0 subspace, okay, then we're going to have the following inclusion spaces. Okay, so first of all, let me explain why this should happen, right? Because this is a nilpotent operator, basically everything will eventually get mapped to 0. So at some point, the range will end up being all of 0. Okay, so the what you want to think about this is pictorially is like you have your 0 space, right? There's your 0 space, and it's a little subspace. And then you have, it contains the range of n to the m. So that's our next space. And then we have, that's contained inside of the range of nm minus 1. Okay, and we keep doing this, all right? Dot, 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 dot. And then you have the first range of n. And then this is all contained inside of the vector space V, right? So you have V. So you have V, when you apply n, you're getting a smaller space, and then you get a smaller space, and then a smaller space, and smaller space, and then it kind of shrinks down to 0. Okay, and here's how the proof works. Okay, so the idea behind the proof works as follows. Okay, and I already started it over on the next page. So let me go to the next page, and I'll kind of explain what happens. Okay, so first of all, you want to find a basis for range nm. So if I go to my picture, you find a basis for this part right here. Okay, now all of those things are inside of these things, right? So what you first want to do is you want to use this basis for the range of m, and then use this to make a linearly independent set inside of the range of nm minus 1. So you take the basis, and somehow you don't use that exact same basis, but you use those elements to build linearly independent elements in the range of this space. Okay, so we're kind of taking this, building something inside of this. Okay, so we use this basis to make a set of linear independent elements. Okay, and maybe we can say, let's call them U1 up to UT. Okay, then what we do is we extend this basis to a basis of the whole space. Okay, so we have the things that are linearly independent that we build from below, and then we add in, say, maybe our new vectors. Okay, so going to our picture, we take some things here, we build linearly independent things inside of the range nm, we extend it to a basis. But now, this isn't what really necessarily we have to do. We have to tweak these things that we added. So tweak the bases so the extended elements get sent to 0. get sent to 0 by n. Okay, so we get a new basis, u1 up to ut, and then v1 prime up to vr prime. Now what the book is doing is it's kind of explaining kind of what is this basis and how you tweak it. So what I'm trying to do here is give you kind of the broad strokes of how the proof works. Okay, so now what you've done is you now have a basis for range n to the m minus 1. But now what you want to do is you want to repeat this process. You take those elements and you build linearly independent elements in the range of n to the m minus 2. You extend that basis and then you tweak it so that the extended things get sent to 0. Okay, and then you keep doing this, right? So you get it up to the range n, you extend it to v, and you make sure that those things you extended get sent to 0. And what you've done is you built your basis by looking at all of these subspaces. And you stop when you get a basis of v. And when you're building these extensions, right? When you're going from a basis and then you're building a new linear independent element, what you're doing, one way to approach it is exactly these sorts of things right here. So V1 through V2, Vn are actually the, I think, yeah, these are the basis elements that you get. Sorry, let me back up. This term, all the ones with the highest exponents are the basis of the range that you start at the smallest thing. And these are the ones that you're extending, okay? And so when you look at the book, you will explain why these particular values are used. But what they're really doing is following this procedure, okay? They're following this main idea of taking something here and building a basis here, and then building a basis there. So you're backfilling, you're kind of expanding it slowly. And if you want, you might want to compare this to the proof where we figured out that you could find a basis so that we have upper triangular matrices. There, we kind of were doing the same sort of thing. We were looking at the null space of n. It's contained inside of the null space of n squared, which was all the way up to the null space of n to the m plus 1, which is equal to v. What we did there, we extended a basis of the null space of n to the I to the null space of n to the I plus 1. So the idea is the same. In this result, when we're doing upper triangular matrices, we looked at all of this kind of growing sets of subspaces of null spaces, and we kind of built the basis of this to build the basis of this, and used the basis of this to build up. When you're doing this proof here, decides instead of using the null space inclusions, it uses the range. So the range of this is included in this, and we build it up this way. So that's kind of the thing that you want to keep in mind. Okay, so this is basically where we've reached the end of chapter 8. We've learned now kind of a nice special basis for an operator. We've learned about the Jordan form, and we've learned that for every linear operator over a vector space, there is a basis that gives a Jordan basis of your vector space. Now, as I said, I have an extra lecture to kind of complement today where I actually will work out all the details of finding a Jordan form in case you're curious. Now, it's not something you will be specifically responsible for, but I did want to have a chance to show you all the worked out examples. So I hope you at least take a minute and maybe spend 20-30 minutes and watch it. It may actually also help you understand how this proof works. So I think that's it for chapter 8. The next kind of lecture 26, will bump back to an earlier chapter where we're going to learn about inner product spaces. That's it for today. Have a great day.